Okay, pushing on. It's my pleasure to be here on behalf of the SARDI Oceanography Group today, presenting to you some recent, current and a little bit of the future direction of the work that we're doing to help support fisheries and aquaculture in the state. I have some animations, so I'm going to hide behind the desk so that I can stay in full control. Okay, so I guess in terms of natural resource management, the Oceanography Group's mission statement is to undertake physical and biological oceanographic research to understand the ecosystems that underpin aquaculture and fisheries and to help their sustainable development. So we kind of have two major roles that we play. One is going out into the field and collecting data and using that data to better understand the ecosystems that are contained within the state's waters. And the other one is to then integrate that field data into developing models, because our models do a very good job of interpolating in space and time and also give us a tool to look at various scenarios without having to go out to the field to do that. So we use those twofold approach of fieldwork and modelling to provide a number of outcomes and support to both government departments. We work closely with PIRSA Fisheries and Aquaculture and other industries, as we can see here, a range of fisheries and aquaculture. Okay, so as I mentioned, the fieldwork is key, both to developing models and gaining a better understanding of our systems. And both the Oceanography Group and our knowledge of our local marine environment gave a huge kick in with the development of the Integrated Marine Observing System. So this is a national system, and South Australia has one node. And so we're mainly based off Kangaroo Island here, and we have a number of different observing platforms. We have a number of consistent moorings which are taking information on physical and biological characteristics, temperature, salinity, amount of dissolved oxygen, chlorophyll biomass as a proxy for phytoplankton biomass, and the ocean currents out there, as well as a number of other observing systems, acoustic observatories, and I believe there's another one off of Kangaroo Island at the moment, listening to whales and cetaceans. We use a number of automated gliders that take physical and biological information along the shelf slope. Simon Goldsworthy's group runs the tag predators, which are collecting environmental information. There's ATEMs and receivers that some of our shark researchers use to have a look at the movement of larger animals as well. So this system's been in place since 2008. And particularly, there's a national reference station here off the tip of Kangaroo Island where we have long-term time series now of many key physical and biological parameters going back to 2008. So this type of information that we get plays a huge role in us being able to develop the capacity to build ocean models. Okay? And starting off with hydrodynamic models that summarise the dynamic features of our oceans, and we can look at things like the circulation features. And we start off at a large scale when we're developing these, and we can see here an example of two models. They both have a different spatial extent, one going out further west as compared to this one here. We have temperature fields here and salinities for the same models. These are embedded within global models, and we can see the boundaries here. And inside is what we model ourselves. So I'll just press play and that can run through. And you can see the seasonal features in our systems. As you can see, when we get to our Gulfs and our more coastal regions, with a limited resolution of in the order of a few kilometres, we can't resolve a lot of the nearshore coastal processes that involve many of the human inputs and some of the finer scale fisheries and aquaculture questions that we're interested in. So I'm just cautious of time, so we're going back through now and warming up into summer. There we go. So that's an example of some of our larger scale ocean models that we've built at SARDI. And then we get into applications of those models. A recent project we had was looking at the carrying carrying capacity of finfish aquaculture, which is located in Spencer Gulf. We have a map of the Gulf here, and at the time of the study over 2010 and 11, we have the bulk of our tuna and yellowtail kingfish aquaculture in Port Lincoln, and there were small hotspots of yellowtail kingfish around Arno Bay and Fitzgerald Bay at that time. We also have, so the problem essentially with the aquaculture is they're fed, there's an intense amount of biomass there where they're fed, and that feed, through some of Milena Fernandez's work, she developed a nutrient budgeted around that. That feed goes into the fish. There's a small proportion, approximately 15%, which is solid waste, which drops pretty well directly beneath cages and has an impact on the benthic environment there. But most of this feed goes into a dissolved pool and releases nutrients into the water column, which we term has a far-field effect. They're washed away, they're diluted by the mixing processes in the ocean, and they're washed away by the currents in the system, and their impacts are often far away from the cages themselves. So this project was about understanding those impacts, the pathways, and what it meant, what was the overall carrying capacity in an ecological sense, both for the Gulf as a whole and also in more local scales as well. So we undertook a year of observations around the Gulf at many of these sites that we can see here to collect the ecological information that we need to build the models, to test the models, and also to just to gain a better understanding of the system. So the first role in that is having a look at the connectivity, because we want to understand the far-field effects of these nutrient sources. And I mentioned that the model also has nutrient sources from other major industries in the area, so wastewater treatment plants and the one still operation. But I'll just play you an annual cycle of the circulation in Spencer Gulf. On the left here we have our temperature field, and on the right we have bottom salinity. The Gulf's always, evaporation always exceeds precipitation in Spencer Gulf, and particularly in the shallow waters up north here, we always have high evaporation, meaning the formation of very salty water. Okay, and we begin our animation in July, and you can see that the Gulf is quite cold throughout. I think we've got a scale of about 14 degrees to about 28 up the top. So I'll just play the animation. So as we come through into the warmer periods, you'll see a build-up of salt, and you'll see the Gulf begin to warm up. Okay, and I'll just very carefully pause it. Okay, now we're in late February, so we're in the peak of summer, and we can see the temperatures got very warm in the Gulf, and there's a strong gradient across the mouth of the Gulf. This temperature front essentially acts as a barrier preventing exchange with the shelf waters where there's upwelling on at this time of the year. So there's limited exchange across the Gulf, and we can see this pile up of salty water in the Gulf. What we find then is as the winter begins to cool, this very salty water becomes even more dense, and because of the rotation of the Earth, it essentially hugs the eastern side of the Gulf and forms a huge density current which outflows. As it outflows, you'll see in the animation, water has to be drawn up inside the Gulf, and this is the annual flushing mechanism of the Gulf. So I'll just let that play through. So as we start to cool down in late autumn, a bit of feedback there, and we can see the dense water flushing out of the Gulf. So that gives you a bit of an overview of the annual circulation features of the Gulf, and it's very important to get your hydrodynamic modelling right before you want to learn, move on to any other type of biogeochemical modelling, which I'll show you now. So keep in mind those circulation features. And then we went on to a biogeochemical model. The beauty of the ROMS ocean modelling platform that we use, it's a community-based open source model system, and there's many bolt-on models that you can pick up off the shelf. The key then is going out and collecting the appropriate data to tune those models for your environment, and make sure you choose the models that are correctly representing the processes that affect your environment. So here is an example of ammonium on the left here, And you can see here, this is where most of the aquaculture is concentrated. So the feeding of our finfish aquaculture here is a nutrient source of ammonium, and we can have a look at the phytoplankton response. This model also has a field for nitrate, which also fuels phytoplankton growth. So not all the growth you see here is directly related to only ammonium, but it is is all part of the circulation process. Okay, so here we can see, we can simulate the nutrients coming in from various sources in the Gulf and have a look at the phytoplankton response, okay, as we go through the annual cycle. I'll just move on because I'm running out of time. A good feature of this is for managers, we're able to package these kind of results into a management tool and give them a user interface that they could use to look at the Gulf as a whole or zoom in on certain areas. And here we have some model output of flushing times, and you see the Boston Bay region is very poorly flushed, getting up around 10 hours to flush a typical lease site. And then managers can use this to have a look at various scenarios at what the given nutrient levels are and adjust their feed rates around a lease relative to some prescribed water quality concentration that they want to keep within. Okay, other applications that we've been able to do is help the prawn fishery. They do surveys of the number of eggs through Spencer Gulf. The problem is the harvest season before Christmas is when they're spawning, so they don't want to have an impact on the next year's stock. So being able to use that Spencer Gulf model to look at prawn recruitment. Here's two different scenarios where we have prawns if they're just washed around by the currents. This scenario, we give them some biological behaviour where they can migrate throughout the water column. What you see here in the green is the successful prawns that make it to the nursery grounds. So I'll move on from there. As you can see, it makes a big difference, and the managers are overlaying their egg surveys with this type of information to better develop harvest strategies. We're also going to be able to suck in information from the sardine surveys that they have to estimate the amount of sardine biomass. Each year they go out and they take surveys on this type of grid that you can see here, and they measure environmental parameters. We've been able to put that information into what was called a statistical model called a general additive model, and this then breaks down individual parameters to give you predictions of what's controlling their distribution. As you can see here, there's a high probability of finding an egg with depth, and in particular a small temperature range, just under there. And the background here shows the probability of finding an egg overlaid with the environmental data, and red being there were no eggs found, and blue being that there were eggs present. So we have a predictive capability that the managers are now using to better refine their samplings to get sampling surveys to get better estimates of biomass for the fishery. So just quickly moving on to the future, we've now got a project through the FRDC where we're partnering with the Bureau of Meteorology to develop nowcast and forecast models for the state. Essentially what will happen is we'll read in information from Bureau of Meteorology products to be able to develop regional scale models for the state, and then we'll be able to again break down and nest down from these large scale models to smaller scale models. There's a huge emphasis on Spencer Gulf, but we're also looking at developing models for Gulf St Vincent and smaller regions like Coffin Bay as well. So I think that's a little bit it. Of course, there's a number of bolt-on models that we can use, and we're looking at with those models to go into seagrass modelling and shellfish modelling as well. So that's a little bit of what's coming up in the future. So thank you for listening, and thank you to our funding bodies and the industry groups and government partners that we work with in delivering this work.
Thanks, Mark. One quick question if it's got a quick answer.
You won't get one from me.
I've got one. The drivers for these models in St Vincent Gulf and the rest of the state, could you tell us a little bit about the application of those in the Gulf St Vincent, the new model you just put up?
In the drivers?
Well, what's driving the need for the model,
Oh,
not
okay.
the physical drivers?
There's a number of drivers, especially when we get into these, the nowcast and forecasting, the biosecurity applications in terms of harmful algal blooms. We've had the POMS epidemic recently. For the industry, there's a need to optimise their shipping routes. So if they can better optimise their pathways that they're doing for shipping. Of course, there's a need along the Adelaide coastal waters. There's a lot of interest in seagrasses and the impacts of us on seagrasses, amongst other things. So there's a whole range of things there that could go. And I noticed with Heidi's work there today, models such as the ones that we're developing here would be very useful in determining characteristics of the environment that you might want to do your oyster or your shellfish restoration exercises in as well.
Great. Thanks very much, Mark.
Excellent. Thank you.